Welcome to Science Snippets Fun Facts and Trivia. Today, we bring you: does the ninth planet of the solar system exist? Unraveling the universe's biggest mystery. The history of Planet 9. 1. What happened to Pluto? Pluto, a name that once resonated with pride as the ninth planet of our solar system. But in 2006, Pluto's status was dramatically redefined. It was no longer a planet but a dwarf planet. This decision didn't just shake the world of astronomy. It sparked widespread public debate and even a sense of loss among those who grew up with 9 planets in their textbooks. So, what really happened to Pluto? And why was it reclassified? Let's delve into the fascinating story. Pluto was discovered in 1930 by American astronomer Clyde Tombaugh at the Lowell Observatory in Arizona. At the time, astronomers were on a quest to find a mysterious Planet X, which was believed to influence the orbits of Uranus and Neptune. When Tombaugh identified Pluto, it seemed to fit the bill, even though it turned out to be much smaller than initially expected, only about 1/6 the mass of Earth's moon. Despite its size, Pluto was celebrated as the 9th planet of our solar system, capturing imaginations for decades. However, the 1990s brought new challenges to Pluto's planetary status. Astronomers began discovering other objects in the Kuiper Belt, a region of icy bodies beyond Neptune. These objects were similar in composition to Pluto, and some, like Eris, discovered in 2005, were even larger. This raised a fundamental question: if Pluto is a planet, should these other bodies also be classified as planets? The scientific community realized that the definition of a planet needed to be revisited. In 2006, the International Astronomical Union (IAU) held a landmark meeting to resolve this issue. They introduced a new, 3-part definition of a planet. According to the IAU, an object must meet the following criteria to be classified as a planet. 1. It must orbit the Sun. 2. It must have enough mass for its gravity to shape it into a nearly round form. 3. It must have cleared the neighborhood around its orbit, meaning it dominates its region of space by either consuming or gravitationally controlling nearby objects. Pluto met the first 2 criteria but failed the third. Its orbit intersects with that of Neptune, and it shares its space with numerous other Kuiper Belt objects. As a result, Pluto was reclassified as a dwarf planet. This decision was not without controversy. Some astronomers argued that the definition was too restrictive, while others pointed out that the decision to reclassify Pluto was made by a relatively small group of scientists. Despite its reclassification, Pluto continues to fascinate us. In 2015, NASA's New Horizons mission provided breathtaking images of Pluto's surface, revealing mountains of ice, plains of nitrogen, and evidence of geological activity. These discoveries remind us that Pluto is far from a demotion. Instead, it represents a gateway to understanding the diversity of objects in our solar system. In the end, the story of Pluto highlights how science evolves. It shows that our understanding of the universe is not static, but grows as we gather new evidence and develop better tools. While Pluto may no longer be the 9th planet, it remains a celestial body of great importance and intrigue, proof that even the smallest worlds can leave a big impact. 2. Early theories of a mysterious planet. The concept of a hidden planet lurking in the outer reaches of our solar system is not new. Long before the hunt for Planet 9, astronomers speculated about the existence of a mysterious world influencing the motions of known planets. These early theories laid the foundation for the search. That continues to this day. The idea of an undiscovered planet began in the 19th century, as astronomers meticulously tracked the orbits of Uranus and Neptune. They noticed discrepancies, tiny deviations in their expected paths, that couldn't be explained by known physics. These anomalies hinted at the gravitational pull of an unseen object, a so-called Planet X. At the time, the search for such a planet seemed not just plausible but inevitable. In the early 20th century, this quest gained momentum. Percival Lowell, an American astronomer and founder of the Lowell Observatory, was particularly passionate about finding Planet X. He dedicated years of his life to studying these orbital irregularities, and meticulously mapped the regions of the sky where the planet might reside. Although Lowell never found his elusive planet, his efforts paved the way for Clyde Tombaugh's discovery of Pluto in 1930. When Pluto was first identified, it seemed to fulfill Lowell's dream. But as we discussed earlier, Pluto turned out to be much smaller than anticipated. It simply didn't have enough mass to account for the observed anomalies in Uranus and Neptune's orbits. This left the mystery of Planet X unresolved. In the decades that followed, new observations and technological advancements challenged the original assumptions. By the 1990s, researchers realized that the supposed deviations in planetary orbits might have been miscalculated due to errors in early measurements. This initially dampened enthusiasm for the existence of Planet X. However, a twist in the story reignited interest in the search for another hidden world. In 2016, astronomers Konstantin Batygin and Mike Brown of the California Institute of Technology published a groundbreaking paper. They presented compelling evidence that a massive, unseen planet might still be lurking in the distant reaches of the solar system. Unlike the older theories, their work wasn't based on orbital anomalies of the inner planets, but rather on the strange, clustered behavior of small icy objects in the Kuiper Belt. These objects seem to be corralled into unusual orbits, as if influenced by the gravitational pull of a distant, massive planet. Batygin and Brown's calculations suggested that this hypothetical Planet 9 could be 5 to 10 times the mass of Earth and orbit the Sun at a staggering distance, taking up to 20,000 years to complete one revolution. Their research provided a modern and scientifically robust framework for the continued hunt for a hidden planet. The allure of discovering a new planet captures our imagination because it speaks to the vast unknowns still lurking in the cosmos. Early theories of Planet X remind us that scientific discovery is a journey. It is often marked by dead ends, recalibrations, and unexpected breakthroughs, all of which push the boundaries of what we know. 3. Mathematical evidence for Planet 9. In the search for Planet 9, one of the most compelling clues comes not from direct observation but from mathematics. The vast distances and dim light at the outer edges of the solar system make it nearly impossible to spot such a planet with telescopes alone. Instead, scientists rely on calculations and indirect evidence to uncover its existence. Let's explore how mathematics is shedding light on this mysterious celestial body. The story begins with the peculiar orbits of a group of distant objects in the Kuiper Belt. This region, a vast expanse of icy bodies beyond Neptune, has long fascinated astronomers. In 2016, researchers Konstantin Batygin and Mike Brown noticed something unusual. Several Kuiper Belt objects or KBOs exhibited highly elliptical orbits, all tilted in a similar direction. This alignment was strange because, in a balanced solar system, these objects should have random orientations. Batygin and Brown's calculations revealed a potential explanation. the gravitational influence of a massive, unseen planet. According to their models, this hypothetical planet, dubbed Planet 9, could be shepherding these KBOs into their unusual orbits. The mathematics suggested that Planet 9 would need to be a gas giant, roughly 5 to 10 times the mass of Earth, orbiting the Sun at an extraordinary distance of about 400 to 800 times the Earth-Sun distance, or 400 to 800 astronomical units. But how does this work? Imagine tossing small pebbles into a pond. If the pond is undisturbed, the ripples spread out evenly. However, if there's a large, invisible object beneath the surface, the ripples will change direction as they encounter it. Similarly, the orbits of Kuiper Belt objects are like ripples in space, influenced by the gravitational pull of a hidden planet. By studying these distortions, scientists can infer the size, mass, and location of Planet 9. Another intriguing piece of evidence comes from the clustering of these objects' perihelia, or the points in their orbits closest to the Sun. Without an external force, their perihelia would be scattered randomly. Instead, they seem to cluster on one side of the solar system, a pattern that can't easily be explained by known forces. Batigan and Brown's models showed that this clustering is consistent with the presence of a distant planet exerting a stabilizing influence. Mathematics also helps rule out alternative explanations. For example, some researchers suggested that the clustering might be caused by interactions with the galactic tide, the gravitational influence of the Milky Way. However, simulations showed that the effects of the galactic tide are far too weak to account for the observed patterns. This leaves Planet 9 as the most plausible explanation. Of course, no hypothesis is complete without testing. Scientists are now using these mathematical models to guide telescope searches, narrowing down the vast regions of space where Planet 9 might be hiding. The task is daunting. Imagine searching for a grain of sand in a football field, but the precision of modern mathematics gives astronomers a fighting chance. The beauty of this mathematical approach is that it turns the unseen into something almost tangible. By analyzing the dance of celestial objects and the subtle tug of gravity, we catch glimpses of a world that has yet to reveal itself. If Planet 9 exists, its discovery will mark a triumph of human ingenuity, proving once again that mathematics is one of the most powerful tools for exploring the cosmos. Characteristics of the hypothetical planet. 1. What would Planet 9 look like? If Planet 9 exists, what might it look like? While no one has seen it directly, scientists have pieced together a fascinating portrait based on mathematical models and our understanding of planetary formation. Let's take a closer look at the potential characteristics of this elusive world. First, size matters. According to calculations, Planet 9 would likely be a gas giant, much smaller than Jupiter or Saturn, but still significant compared to Earth. Estimates suggest it could be 5 to 10 times Earth's mass, placing it firmly in the category of super-Earth or mini-Neptune planets, types that are common in other star systems but absent from our own. Its diameter might range from 2 to 4 times that of Earth, depending on its composition. What about its appearance? If Planet 9 is a gas giant, it would probably have a thick atmosphere composed primarily of hydrogen and helium, similar to Neptune and Uranus. However, given its extreme distance from the Sun, it would be a frigid world. Surface temperatures could plunge to hundreds of degrees below freezing, making it one of the coldest objects in the solar system. This distance from the Sun also means that Planet 9 would be incredibly dim. Unlike inner planets like Mars or Venus, which reflect significant sunlight, Planet 9 would receive so little sunlight that it might only reflect a faint, ghostly glow. This is part of why it has remained so elusive. Telescopes have to search for something that is not only far away, but also nearly invisible against the dark backdrop of space. The planet's orbit adds to the mystery. Models suggest that Planet 9 follows an eccentric, elongated path around the Sun, possibly taking between 10,000 and 20,000 years to complete a single revolution. At its farthest point, or aphelion, it could be as much as 800 astronomical units (AU) from the Sun. That's 800 times the distance between Earth and the Sun. At such distances, sunlight would take more than 4 days to reach the planet. Interestingly, this distant orbit might mean that Planet 9 didn't form in its current location. Some theories suggest it could have been an inner solar system planet that was flung outward by interactions with Jupiter or Saturn during the early chaotic days of planetary formation. Alternatively, it might be a captured planet, an object that formed in a different star system and was later pulled into the Sun's gravitational influence. Finally, the planet's potential moons or rings could offer additional clues. Like Neptune and Saturn, Planet 9 might have a system of moons, or even faint rings orbiting it. These smaller bodies could help scientists better understand the planet's history, including whether it had close encounters with other solar system giants that altered its orbit. In many ways, Planet 9 represents a missing puzzle piece in our understanding of the solar system. Its size and composition might bridge the gap between the rocky inner planets and the massive gas giants, offering a glimpse into how planets form and evolve. Although we can only imagine its appearance for now, the discovery of Planet 9 would open a new chapter in the story of our cosmic neighborhood. 2. The orbit mystery. One of the most puzzling aspects of Planet 9 is its proposed orbit. Unlike the near-circular orbits of most planets in our solar system, Planet 9 is believed to follow an eccentric and elongated trajectory around the Sun. This orbit raises several fascinating questions about how such a planet could exist in this unusual configuration. Let's start with the basics. Planet 9 is hypothesized to orbit the Sun at an average distance of about 400 to 800 astronomical units (AU), where 1 astronomical unit is the distance between Earth and the Sun. To put that into perspective, Neptune, the farthest known planet, sits at about 30 astronomical units. Planet 9, therefore, lies in an almost unimaginable realm of space, hundreds of times farther away. But it's not just the distance that makes this orbit intriguing, it's the shape. Planet 9's orbit is thought to be highly eccentric, meaning it is more oval-shaped than circular. At its closest point, or perihelion, it might come as close as 200 astronomical units to the Sun. However, at its farthest point, or aphelion, it could drift out to 800 astronomical units or more. Such an orbit would take the planet tens of thousands of years to complete one full revolution around the Sun. This eccentricity raises an important question. How did Planet 9 end up in such an unusual orbit? One possibility is that the planet formed closer to the Sun, like the other giant planets, but was later ejected outward. In the chaotic early solar system, gravitational interactions between Jupiter, Saturn, and other large bodies could have flung Planet 9 to its current distant trajectory. Another theory suggests that Planet 9 might not be a native member of our solar system at all. It's possible that it formed around a different star and was later captured by the Sun's gravity. This scenario could explain why its orbit is so different from those of the other planets. The orbit itself also provides clues about the planet's size and influence. For example, the peculiar clustering of certain Kuiper Belt objects the icy bodies beyond Neptune, suggests that Planet 9's gravity is shaping their orbits. These objects appear to be aligned in ways that cannot be easily explained without the gravitational pull of a distant, massive planet. This alignment is one of the key pieces of evidence for Planet 9's existence and helps scientists model its orbit with increasing precision. Interestingly, the tilt of Planet 9's orbit may also have implications for the entire solar system. Some researchers believe that the planet's off-kilter orbit could be slightly tilting the rest of the solar system in response. This tilt is subtle, but it provides yet another clue about the planet's location and mass. Finally, the orbit mystery underscores why Planet 9 has been so difficult to detect. At its aphelion, the planet would be incredibly faint, reflecting only a tiny amount of sunlight. Even the most powerful telescopes would struggle to spot it against the vast darkness of space. However, its eccentric orbit offers hope. As the planet moves closer to perihelion, it will become brighter and easier to observe. The orbit of Planet 9 is not just a riddle. It's a window into the dynamic history of our solar system. Whether it was flung outward, captured from another star, or shaped by ancient gravitational encounters, its trajectory holds secrets about the forces that sculpted our cosmic neighborhood. Solving this mystery could reveal not only the truth about Planet 9, but also the untold story of how our solar system came to be. 3. Comparison with other solar system giants. If Planet 9 exists, how does it compare to the other giant planets in our solar system? Jupiter, Saturn, Uranus, and Neptune have long dominated our understanding of gas giants and ice giants, setting the benchmarks for size, composition, and behavior. Let's explore how Planet 9 might fit into this family of giants and what makes it unique. First, consider size. Planet 9 is estimated to be 5 to 10 times the mass of Earth. While this makes it significantly smaller than the gas giants, it's still much larger than any of the terrestrial planets, like Earth or Mars. In fact, Planet 9 would be classified as a super-Earth or mini-Neptune, a category of planet that is common in other star systems, but missing from our solar system, at least so far. Next, we turn to composition. Based on its likely mass and location, Planet 9 would probably be more similar to Uranus and Neptune than to Jupiter or Saturn. Uranus and Neptune are often called ice giants because their compositions include large amounts of water, ammonia, and methane, in addition to hydrogen and helium. Planet 9, being in the frigid outer reaches of the solar system, would also likely have a significant proportion of these ices frozen solid due to the extreme cold. The planet's density might also differ from that of the inner gas giants. Jupiter and Saturn are composed mostly of hydrogen and helium, making them relatively low density despite their massive size. Planet 9, with its smaller mass, could have a greater proportion of heavier elements, giving it a higher density overall, closer to that of Neptune or Uranus. Another interesting comparison is the planet's atmosphere. Due to its extreme distance from the Sun, Planet 9's atmosphere would be incredibly cold, potentially hundreds of degrees below freezing. This contrasts sharply with the dynamic, swirling storms of Jupiter or Saturn, which are powered by internal heat and sunlight. Instead, Planet 9's atmosphere might be calm and stable, with little energy to drive dramatic weather patterns. When it comes to orbits, Planet 9 is a complete outlier. Jupiter, Saturn, Uranus, and Neptune all follow relatively circular orbits in the same plane as the rest of the solar system. In contrast, Planet 9's orbit is thought to be highly elongated and tilted, stretching far beyond the paths of the other planets. This unique trajectory not only sets Planet 9 apart, but also suggests that it experienced a very different evolutionary history compared to its fellow giants. Gravitational influence is another key factor. Jupiter, the king of planets, exerts a tremendous gravitational pull that has shaped the orbits of many asteroids and comets. Saturn's gravity is responsible for its stunning ring system, while Neptune has shepherded objects into the Kuiper Belt. If Planet 9 exists, its gravity would likely play a similar role, sculpting the orbits of smaller bodies in the distant reaches of the solar system. In fact, this gravitational influence is one of the strongest pieces of evidence supporting the planet's existence. Finally, the discovery of Planet 9 would add a missing piece to the puzzle of planetary diversity. While the inner planets are rocky and the outer planets are gaseous or icy, Planet 9 might represent an intermediate type, a super-Earth or mini-Neptune that helps bridge the gap between these categories. This would make it not just a new addition to our solar system, but also a valuable case study for understanding planets in other star systems. In summary, Planet 9 would share some characteristics with the known giants of the solar system, such as its likely icy composition and gravitational influence. However, its unique orbit, smaller size, and potential status as a super-Earth make it stand out. If confirmed, Planet 9 would not only expand our view of the solar system, but also deepen our understanding of the incredible variety of planets that exist in the universe. How scientists are searching for Planet 9. 1. Advanced telescopes and technology. Searching for Planet 9 is one of the most challenging endeavors in modern astronomy. Why? Because Planet 9, if it exists, is incredibly distant, faint, and slow-moving. Spotting such an elusive target requires cutting-edge telescopes and sophisticated technology. Let's explore the tools scientists are using to uncover this hidden world. The first challenge is distance. Planet 9 is hypothesized to be located hundreds of astronomical units AU from the Sun, far beyond the reach of conventional observation methods. At these distances, the planet would reflect only a tiny fraction of sunlight, making it extremely dim, perhaps millions of times fainter than the faintest stars visible to the naked eye. To overcome this, astronomers turn to the most powerful telescopes on Earth and in space. One key player in the search is the Subaru telescope, located atop Mauna Kea in Hawaii. With its massive 8.2-meter mirror and advanced imaging capabilities, Subaru is uniquely equipped to scan vast areas of the sky at high resolution. Astronomers use this telescope to systematically survey the regions of space where Planet 9 is most likely to be found. Subaru's sensitivity to faint objects makes it an ideal tool for detecting the subtle light reflected by a distant planet. Another critical tool is computational power. Observing the sky generates an overwhelming amount of data, millions of images that must be analyzed for any signs of Planet 9. Modern algorithms and machine learning techniques play a crucial role in processing this data. These programs can identify patterns and anomalies that might otherwise be missed by human eyes, narrowing down the search field. Space-based telescopes also contribute to the effort. Instruments like the Hubble Space Telescope and the James Webb Space Telescope are designed to capture incredibly detailed images of distant objects, while their primary missions focus on galaxies and exoplanets. These telescopes can also be used to investigate the faint glow of potential solar system objects. The advantage of space-based telescopes is that they avoid the distortion caused by Earth's atmosphere, offering a clearer view of the cosmos. Another exciting development is the upcoming Vera C. Rubin Observatory, set to begin operations soon. This state-of-the-art facility will conduct the Legacy Survey of Space and Time LSST, a 10-year project that will produce the most comprehensive map of the night sky ever created. With its ability to repeatedly image the same regions of space, the Rubin Observatory could detect the slow, consistent motion of a distant object like Planet 9. Scientists also rely on indirect methods to refine their search. For example, they study the orbits of Kuiper Belt objects KBOs, whose unusual behavior suggests the presence of a distant planet. By analyzing the gravitational effects that Planet 9 might have on these objects, researchers can predict where the planet is most likely to be located. This strategy helps focus telescope observations on specific regions of the sky, increasing the chances of success. Despite these technological advances, the search is far from easy. At the vast distances involved, even the best telescopes can struggle to detect a planet that might be no brighter than a faint star. Complicating matters further, the planet's slow movement across the sky makes it difficult to distinguish from background stars and galaxies. Patience and precision are key to overcoming these challenges. In many ways, the search for Planet 9 is a testament to human ingenuity. By combining powerful telescopes, cutting-edge algorithms, and the collective efforts of astronomers worldwide, scientists are pushing the boundaries of what is possible. Each observation, each dataset, brings us one step closer to solving the mystery. And if Planet 9 is out there, these tools will be the ones to find it. 2. Challenges in finding a hidden planet. The search for Planet 9 is as daunting as it is exciting. Despite significant advancements in technology and methods, several challenges make finding this elusive world an incredibly complex task. From the vastness of space to the planet's faint glow, let's examine the obstacles standing in the way of discovery. The first and most obvious challenge is distance. Planet 9 is believed to orbit far beyond Neptune, at a distance of 400 to 800 astronomical units AU from the Sun. To put that into perspective, Neptune is about 30 astronomical units away, and the Voyager 1 spacecraft, the farthest human-made object, is around 160 astronomical units from Earth. At such extreme distances, Planet 9 would receive only a fraction of the sunlight that reaches Earth, making it one of the darkest objects in the solar system. This brings us to the second challenge: its faintness. The further a planet is from the Sun, the less light it reflects, and Planet 9 is no exception. Even with the largest and most sensitive telescopes, detecting such a dim object is like searching for a single grain of sand on a vast beach, an endeavor requiring immense precision and patience. Adding to the difficulty is the planet's motion. Unlike stars, which appear relatively fixed in the night sky, planets slowly move against the backdrop of distant stars and galaxies. However, Planet 9's movement is so slow, due to its vast orbit, that it could take years of observations to detect its gradual shift in position. This makes distinguishing the planet from background objects a painstaking process. Another complication arises from the sheer size of the search area. Astronomers don't know exactly where Planet 9 might be located in its enormous orbit. Current estimates suggest it could lie in a region of the sky spanning tens of thousands of square degrees. To cover this vast area, astronomers must rely on wide-field surveys, which are time-consuming and generate massive amounts of data. Analyzing this data requires both powerful algorithms and human expertise. Moreover, there's the possibility of false positives. Many objects in the Kuiper Belt and beyond can mimic the characteristics of Planet 9, such as reflecting faint light or exhibiting unusual movement. Distinguishing between these smaller objects and a true planet demands rigorous follow-up observations, further complicating the search. Interestingly, even the planet's potential orbit adds to the challenges. Planet 9's hypothesized eccentric orbit means it could spend the majority of its time at its farthest point from the Sun, or aphelion. If it happens to be near this distant part of its orbit, it would be even fainter and harder to detect, making the task feel almost impossible. Finally, there's the issue of time and resources. Observing the distant reaches of the solar system requires not just advanced telescopes, but also long observation periods and significant funding. Astronomers often have to compete for access to the best telescopes, balancing their search for Planet 9 with other high-priority scientific projects. Despite these hurdles, the search continues with determination. Each new technological advancement, from improved telescopes to machine learning algorithms, brings us closer to overcoming these obstacles. The challenges may be enormous, but so is the potential reward. Confirming the existence of a ninth planet would be a monumental discovery, reshaping our understanding of the solar system and its formation. For now, Planet 9 remains hidden, but its mystery is a powerful motivator. It's a reminder that even in our modern era, there are still vast frontiers left to explore, and that some of the universe's greatest secrets lie just beyond our reach. 3. Current progress and discoveries. The search for Planet 9 is an ongoing scientific adventure, filled with exciting progress and intriguing discoveries. While the planet itself remains hidden, astronomers have uncovered significant clues that keep the hunt alive. Let's take a closer look at what's been achieved so far, and what might come next. One of the most compelling developments comes from the detailed analysis of Kuiper Belt objects (KBOs). These distant, icy bodies orbit the Sun beyond Neptune, and are strongly influenced by gravitational forces in the outer solar system. Over the years, researchers have noticed peculiar patterns in the orbits of certain KBOs. Instead of being randomly distributed, many of these objects exhibit a strange clustering effect. Their orbits align in a way that suggests they're being shepherded by the gravitational pull of a massive, unseen planet, likely Planet 9. In 2016, Konstantin Batygin and Mike Brown at the California Institute of Technology published a groundbreaking study on these orbital anomalies. Using advanced simulations, they demonstrated that the observed clustering could be explained by the presence of a planet, approximately 5 to 10 times the mass of Earth, orbiting the Sun at a vast distance. This study reignited global interest in the Planet 9 hypothesis and provided a scientifically rigorous foundation for continued exploration. Since then, researchers have refined their models to better predict where Planet 9 might be located. By studying the gravitational influence on other KBOs and even distant comets, astronomers have narrowed down the regions of space most likely to host the elusive planet. These efforts help guide observational campaigns, ensuring that telescopes are focused on the most promising parts of the sky. Another important development is the role of technology. Telescopes like the Subaru telescope in Hawaii and upcoming instruments like the Vera C. Rubin Observatory are equipped with advanced capabilities to scan vast areas of the sky with unprecedented precision. These tools allow scientists to systematically search for Planet 9's faint signature, slowly eliminating regions of space where it might be hiding. Interestingly, the search for Planet 9 has also led to other discoveries. In their quest to uncover the planet, astronomers have identified dozens of new Kuiper Belt objects, some of which are among the largest ever found. These discoveries not only enrich our understanding of the outer solar system, but also provide additional clues about Planet Nine's influence. Despite this progress, the search is far from over. Astronomers are now exploring alternative explanations for the observed orbital anomalies. Could these patterns be the result of interactions with a distant population of smaller objects, rather than a single massive planet? Or could they be caused by influences from outside the solar system, such as the gravitational pull of the Milky Way? These questions highlight the need for continued observation and analysis. One of the most exciting prospects lies in the future. With the advent of the Vera C. Rubin Observatory and its Legacy Survey of Space and Time, LSST, scientists will soon have access to a treasure trove of data. The observatory's ability to repeatedly image the same regions of the sky over a decade will make it easier to detect the slow motion of a distant object like Planet 9. If the planet exists, this next generation of technology might be what finally reveals it. In the meantime, the hunt for Planet 9 remains a global effort, involving collaborations between researchers, institutions, and even amateur astronomers. Every new discovery, no matter how small, brings us closer to solving the mystery. The progress made so far is a testament to human curiosity and determination. While the journey to find Planet 9 is still underway, the discoveries along the way remind us why we search to understand the unknown and to expand the boundaries of our cosmic knowledge. Implications of Planet 9's discovery. 1. Redefining the solar system. The discovery of Planet 9 would be one of the most profound milestones in modern astronomy. It wouldn't just add another planet to the solar system. It would fundamentally change how we understand our cosmic neighborhood. Let's explore how finding this elusive world could redefine the solar system as we know it. For over a century, the solar system has been presented as a well-organized collection of planets orbiting the Sun in near-perfect harmony. From Mercury to Neptune, each planet fits neatly into the categories of terrestrial or gas giants. The demotion of Pluto in 2006 to a dwarf planet reinforced the idea that the solar system was complete. 8 planets, no more, no less. But Planet 9 challenges that assumption. If confirmed, Planet 9 would expand the boundaries of the solar system in ways we never imagined. Its estimated orbit, stretching hundreds of astronomical units AU from the Sun, would place it far beyond Neptune and the Kuiper Belt. This would redefine the outer limits of our solar system, extending its reach into a region that was previously considered empty space. It would also prompt us to reconsider the criteria for what constitutes a planet, particularly in such a vast and dynamic environment. Planet 9 could also help solve lingering mysteries about the solar system's formation. For example, its existence might explain why some Kuiper Belt objects and distant comets follow highly unusual orbits. These objects seem to be influenced by a massive gravitational force, and Planet 9 could be the missing piece that ties these anomalies together. Beyond reshaping our understanding of the solar system's structure, discovering Planet 9 could influence how we search for planets in other star systems. Astronomers have already identified thousands of exoplanets, many of which fall into the categories of super-Earths or mini-Neptunes. Yet our own solar system lacks these types of planets. If Planet 9 turns out to be a super-Earth or mini-Neptune, it would bridge this gap and provide valuable insights into how such planets form and evolve. Another fascinating implication is how Planet 9 could affect future exploration. Just as the discovery of Pluto inspired decades of research into the Kuiper Belt, Planet 9 could open up new areas of study. In the distant reaches of the solar system, missions might be designed to explore not only the planet itself, but also its potential moons, rings, and any nearby objects it influences. On a cultural level, finding Planet 9 would reignite public fascination with the solar system. It would mark the first discovery of a new planet since Neptune in 1846, capturing the imagination of people worldwide. For a generation that grew up with 8 planets, the addition of a 9th would be a momentous event, sparking curiosity and inspiring future astronomers. In many ways, Planet 9 represents more than just a new member of the solar system. It challenges our assumptions about what's out there, and reminds us that the cosmos is full of surprises. Its discovery would symbolize humanity's relentless quest to uncover the unknown, and would mark the beginning of a new chapter in our exploration of the solar system. 2. Impact on astronomy and physics. The discovery of Planet 9 wouldn't just reshape our understanding of the solar system. It could have profound implications for the fields of astronomy and physics. From redefining planetary dynamics to challenging existing theories of the universe, the impact of such a find would be far-reaching. One immediate effect would be on our understanding of planetary formation. Current models suggest that planets form relatively close to their host star, where gravitational forces can coalesce gas and dust into large bodies. Planet 9, however, resides in a region of space so distant and cold that traditional planet formation theories struggle to explain its existence. Its discovery would likely force scientists to refine or even rethink how planets form, especially in the outer reaches of a star system. Planet 9's orbit would also offer new insights into the chaotic, early history of the solar system. The planet's highly eccentric and tilted path suggests it may have been flung outward by gravitational interactions with other giant planets, such as Jupiter or Saturn. Alternatively, it might have originated outside our solar system and been captured by the Sun's gravity. Either scenario would provide valuable data about the forces and events that shaped the solar system billions of years ago. Another fascinating possibility is that Planet 9 could help us test fundamental laws of physics. For example, the planet's extreme distance and gravitational influence might allow scientists to study the behavior of objects in low-gravity environments. It could also serve as a natural laboratory for examining how dark matter, an invisible and mysterious substance thought to make up a significant portion of the universe, interacts with ordinary matter. In addition, Planet 9 could shed light on the structure of the Kuiper Belt and the Oort cloud. These distant regions of the solar system remain largely unexplored, but they hold crucial clues about the solar system's origins. By studying how Planet 9's gravity shapes these areas, scientists could gain a deeper understanding of how icy bodies are distributed and how they interact with other celestial forces. The implications extend beyond our solar system. If Planet 9 turns out to be a super-Earth or mini-Neptune, it would add to our understanding of exoplanets, planets orbiting stars other than the Sun. These types of planets are common in other star systems, but they've been notably absent in our solar system. Finding one close to home would provide a rare opportunity to study its properties up close, offering insights that could be applied to distant worlds. Finally, the discovery of Planet 9 would highlight the importance of collaborative science. The search involves astronomers, physicists, and computer scientists from around the world, working together to tackle one of the most challenging problems in modern astronomy. Their success would demonstrate the power of global teamwork and the role of advanced technology in pushing the boundaries of human knowledge. In many ways, The impact of finding Planet 9 would mirror the discoveries of Neptune and Pluto in earlier eras. Each new planet has forced us to revisit old assumptions and has opened new avenues of exploration. Planet 9 would be no different, providing answers to some of astronomy's biggest questions while raising new ones in its wake. The search for Planet 9 is a reminder of how much we still have to learn about the universe. If and when it's found, it won't just be a triumph for astronomy. It will be a testament to humanity's unending curiosity and drive to understand the cosmos. 3. What could be next? The discovery of Planet 9 would be a monumental achievement, but it would also raise a host of new questions and possibilities. What would we explore next in our solar system? And how would this discovery shape future research? Let's take a look at what could come after Planet 9 is found. One of the first steps would be to learn as much as possible about the planet itself. Once its location is confirmed, astronomers would focus on characterizing its physical properties, such as its size, mass, composition, and atmosphere. High-powered telescopes on Earth and in space would play a crucial role, providing detailed observations of its surface and environment. These studies could reveal whether Planet 9 has moons, rings, or other unique features, adding new layers to our understanding of distant planets. Next, scientists would likely plan a dedicated mission to visit Planet 9. Similar to how the New Horizons spacecraft provided groundbreaking images of Pluto in 2015, a mission to Planet 9 could offer close-up views and direct measurements of its surface and atmosphere. Such a journey would take decades to plan and execute, given the planet's extreme distance from Earth, but the scientific rewards could be immense. Planet 9's discovery would also shift attention to the outer reaches of the solar system. If such a massive planet exists in the Kuiper Belt, it's possible that other, smaller planets or objects are waiting to be discovered. Astronomers might intensify their searches in the region beyond Neptune, using advanced telescopes and space missions to map these uncharted areas. Another intriguing possibility is the study of Planet 9's role in shaping the solar system. Its gravitational influence might offer insights into the dynamics of the Kuiper Belt and the Oort cloud, a vast shell of icy objects surrounding the solar system. These regions hold critical clues about the formation and evolution of our cosmic neighborhood, and Planet 9 could be the key to unlocking their mysteries. On a broader scale, the discovery of Planet 9 would inspire new theories about planetary formation and migration. If the planet formed close to the Sun and was ejected outward, its history could reveal the chaotic interactions that occurred in the early solar system. Alternatively, if it was captured from another star system, it might provide rare insights into how stars exchange material. Either scenario would have profound implications for our understanding of planetary science. Finally, finding Planet 9 would likely fuel the search for similar objects in other star systems. If a ninth planet exists in our solar system, it suggests that distant, hidden planets might also be common in exoplanetary systems. Future missions and telescopes could be designed specifically to search for these elusive worlds, expanding our knowledge of the universe and its diversity. In many ways, the discovery of Planet 9 would be just the beginning. Each new finding would lead to more questions, more exploration, and a deeper appreciation of the complexities of our solar system. It would remind us that even in the vast darkness of space, there are still countless wonders waiting to be discovered. The hunt for Planet 9 captures the essence of science, a relentless pursuit of the unknown, driven by curiosity and a desire to understand our place in the cosmos. If and when we find it, the journey of discovery will only grow more exciting. If you found this video helpful or interesting, please give it a thumbs up and subscribe to the channel.